Is it okay now? Should be fine. Okay, good. Yeah. Last time we introduced gently start of what is a SLAM program, and also we quickly recap some concepts in the probability, the basics of probability theory. We quickly reviewed what is sample space, random variable, and it can be discrete or continuous. And we give some examples, like for a typical application, what problem will be discrete, and what random variables will be normal, like continuous. And then we introduce what is a joint distribution, joint probability, and also emphasize the importance of the joint distribution. Right? Let me switch back to the material. Okay, that's the notes we discussed last time. I want to quickly remind you that this is a whole bunch of discussion we had on the joint distribution, right? Because of the theorem of total probability and the Bayes equation, if you know the joint distribution pxy, then you know whatever combinations, right? Based on the joint distribution, you can know whatever you want. For example, this one, right? So the joint distribution is important. Also, last time we discussed the relation between the diagnostic reasoning and then the causal reasoning. Right? We explained that the Bayes equation is a powerful tool because sometimes you can transform a difficult problem, the solution of a difficult problem, into some question which is easier to answer. Okay, that's basically last week. And then I will create a new slide for today. Okay. A quick reminder is this equation is the key. Right? If you cannot follow last week's lecture, you should at least pay more attention to this equation. Right? Try to understand that from each component to each component. Right? Especially the representation that we can use the total probability theorem and the total probability theorem and also the Bayes equation to transfer this to problems. And also we introduce what is conditional probability. Wait, sorry, I had some problem with cooperation. Again, I see what I see on my screen is not exactly what you see. Okay, and then introduce a covariance of random variable, and we stop at somewhere like the Bayesianism and Friedrichsism, right? Roughly this location. All your previous knowledge about the typical causes in the probability is about frequentism. That means you want to use a frequency or occurrence of events to determine the measure of probability, right? This is a measure of probability. But what we want to adopt in this lecture is more to the side of Bayesianism. Right? But the Bayesianism is all, most cases is about the subjective goals. And that's, in other words, is assumptions of x, right? X can be a state, it can be observation. Okay, we will use the Bayesianism more. Okay, last time we stop somewhere at this example. Right? Suppose you have a robot. This robot needs to know the state of a door, and hopefully there is a sensor at the top of this robot. We call this sensor as Z, and then this Z may have different readings from the as a raw input from the sensor, right? And sometimes you have a measurement small z. I want to remind you that we use small z, the lowercase letters, for the values of random variables, right? This is just a value of random variable z. And then you can understand this equation, the physical meaning of the P open given z. It simply means I want to find out the probability that the door is open given the condition that you have a measurement z. Both open and small z, they are all values, right? These are not a random variable. These are values of a random variable. And searching for the P open given z is called diagnostic reasoning. And this problem really is more difficult to answer based on the discussion, because in this scenario, the z can be any value, right? Given the conditions of the door. But if we want to look at the inverse problem, now you observe a z, the inverse probability that the door is open seems a more difficult problem than the causal reasoning, right? Because the solution for the causal reasoning is I can do experiments, or I can do calibration of the sensor, right? Given the given state, then I can have a set of observations there, right? By joining all these observations, I will have this P. Okay, P is the probability. When I initially learned about the Bayesian, it took me some time to understand what is the P, because I always recall the definition of a definition of the frequentism, right? It seems that I need to do many times experiments, and finally I want to compute the probability based on the occurrence of something happen, right? So gradually, during the study of the Bayesianism, and you will see that the p value here, previously you understand that as the probability, but I want you to consider the p at least during the semester, you want to understand P as a distribution. Right? This is more a distribution than a probability. Okay, so I will spend more time because this is a very important concept, so that can be easily generalized to other lectures. So the P of Z given open means the distribution of the value Z. Okay, Z is a value. Again, this is a value. The distribution of Z given the condition that's the door is open. Okay, that means you can even plot out this distribution. Okay, for example, the distribution of value Z is like this. That means the probability that the observation of Z, the probability that the observation of the Z given some conditions. So finally, you have, for example, you have a continuous function. Right? This is not only the probability, right? This is a complete picture. This is the P of Z. Okay, just pay more attention to this. Often this causal knowledge is easier to obtain. We mentioned that this can be obtained from what? From calibration for the robotic problem, or you can get that by experiment, other experiments. And the Bayes rule allows you to use this causal knowledge, right, to use this causal knowledge to solve a diagnostic problem. Right, solve diagnostic. And you know this part is easy to get as a good experiment. experiment 100 times, 1,000 times. Right? Keep the door open at different angle or whatever, and we will let the robot see to collect the observation Z. And finally, we will have a distribution of Z. Okay, distribution of the Z can be let's say the Z can be a value, maybe it's a Gaussian distributed around around 1. Okay, and this is 1.0. Okay, this is not good. And sometimes during your experiment, maybe the first experiment, you will get a value somewhere around the 1, and then later you will have other observations. And sometimes even the observation is far off. Right? For example, this one is far off your expectation. Right? Your expectation here is 1, and then you collect the probability density. Right? Then you finally have this distribution. Okay, this is the PZ given what? Given the door is actually open. Okay, you have this measurement there. The measurement is like a Gaussian with a mean 1 or 0 and probably some variance of sigma. Okay, it's not updating. Okay, good. That's the idea I want to get. And that distribution. So we copy the previous page to here. That distribution is easy. Right? This is easy. This is easy. And another thing is the so-called.
Professor, sorry, Professor. No, we cannot hear what you're saying right now because you're drawing on your iPad. It's very noisy.
You cannot hear. So how about swap the? Let me swap the microphone to my PC.
Okay.
How about now?
Okay.
Wait. How about now? Better?
Yes, it's better. It's better. Yeah.
Okay, better. Okay, let's use this method. I now I mute my iPad and only turn on the microphone of the PC. Okay. Okay, let's continue. Okay, let's continue. And we mentioned this program is easy to get because you can train that by calibration. And this part is called a prior, right? A prior refers to some prior knowledge, right? The P of open, in this case, we can understand as a probability, right? It's a distribution, but this distribution is a point distribution. We want to only see, or you call it as a marginalized distribution. The P open, you can understand as P open equals to the marginalization over all the Z of this joint distribution P open and Z, right? So again, this is a distribution, just we marginalize out this Z. Good. If this is the case, and then this P open is also a distribution, right? We call this the prior. And this PZ will go open, we get the in red box. This is a so-called likelihood. This is a likelihood. Likelihood just show that given state, your state now is open, right? Given this state, what is the likelihood to have some sensor reading Z? Okay, and then another part, the bottom, this is known as what? This is a probability that you observe this Z in general. Okay, observe this Z in general. But this Z, as I mentioned, it's a value, right? It's a value. It's like you don't care about whether the door is open or closed. Just do a full day or experiment, and you take the value of your sensor Z, and then you plot this out, right? You plot this value out, and finally you have a distribution. Okay, so you can see that this distribution will not change, right? This is not changing, not change, or you can say that regardless the open state, right? Regardless this x, right? No matter whether door is open or closed, this value is not changing. Okay, this value is not changing. So that means the probability of P open given Z is proportional to the products above the bar. Okay, and we know this is the case. Let me give it a name, right? We have PZ, in this case, is evidence. Right? This is called evidence. So it's evidence to show that the sensor is actually working, or during your experiments, what data you have collected. Right? So it's called evidence. And after that, then this P open given Z is what? It's called a posterior. Right? This is a posterior because we have a prior, and with the enhancement of the likelihood under the condition of this evidence, you can also understand this is the experiment, right? This evidence is your experiment. Under this condition, we get a posterior, right? After we do the analysis, we get finally this result, right? That's why it's called a post, right? It's posterior. Okay, so then this is a key to link the diagnostic reasoning with the causal reasoning. So from the equation, it's easy. You already see the Bayes equation many times, right? But now we simply want to explain that if you have the state is x and your observations or your sensor data, right? If this is O, and then what we want to solve, typically want to solve a problem like this, right? I mean, that means we want to infer some states. We want to know the X can be what? Can be, what can be a typical state? Like the robot's location, or some labels for the detection problem, and also some inherent internal states of your system or control system, etc. Right? Basically, that's something valuable, right? You want to infer this knowledge based on your observations, based on this O. Okay, and that's the so-called, this posterior will be the likelihood times this prior over this evidence, right? Over evidence, and it's proportional to the likelihood times prior. Okay. If you look deep into the equation, you will find something more interesting, right? It's a px given O is the PO given x likelihood times P of x, the prior, over PO, proportional to what? Proportional to this guy. And that's nothing else than the joint distribution of O and X. Okay, that means in many cases, your problem has been transferred from the inference of the state to what? To the inference of the joint distribution. Sorry, the inference of the joint distribution. Again, it proves the thing we discussed last week, right? So the joint distribution is always the key for your for inference. Good. Let me see. There is lecture question. This one. As I mentioned, we will have many lecture questions, right? We did the record question last time. Also the three factors, we discussed that. Okay, we can review some of the questions first, so then we answer the new question. So question one, if you still remember, what are true about this model-based agent compared with a reactive agent, right? So A, the model-based agent must be a reactive agent as well. Is this true? If you think this is true, can you click the yes button? Otherwise, you click the no button. On your participants list, there are a series of buttons, right? You see that? Okay. There's a 1 yes, 5 no's. Yes, this is good, right? You have some general understandings. Reactive agents sometimes it's not model-based, right? It's not model-based, but the other way. Model-based agent, is that necessary to be a reactive agent? This is no, right? This is no. Because some model-based agents, you don't even need the preset sensors, right? As long as you have an inherent variable, you don't need to to be reactive to the environment changes. Okay, that's why A is wrong. And B, it requires model-based agents requires relatively more memory and higher CPU cost. Is this true? Can you click yes or no? More memory and also the CPU cost. Yeah, this is the truth, right? Because you need to store the model. You need to store the model. Okay, I will clear all. The C, path planning can only be realized with a model-based agent. Is this true? If you want to plan a path around the environment, path planning can be realized can only be realized with model-based agent. This is true, right? So when you talk about the path planning, that means you already have some ideas about the environment. Right? That's idea of an environment is the model of the environment. Typically, it's a map. Okay, teach and repeat scenario. These are model based. Teach repeat. This is model based. This should be true, right? This should be true because you need to store the states. Otherwise, you don't have a teach phase, right? When you teach, actually, you're teaching a sequence of states. Then you need to store the states, and that's the model. Okay. Question two. Yeah, this comes to the very important recipe, right? So it's typically a tip. Find two ways to decompose a PABC with a conditional probability. How could you decompose this joint distribution PABC? Here I use a random variable, right? Random variable PABC. How could you decompose that? Okay. Can you do this quickly? Maybe take 20 seconds by your own, then I will explain the answer. If you have a quick answer, you can also type in the chat window. How can we decompose that by a series of conditional probability? For example, I can give you one example. PA times PB given A times PC given AB. Okay, this is the one way to decompose. Also, there are many other ways. Okay, and this equation, for example, the one I wrote here, this is true for any kind of conditional assumptions, right? This is just simply true. Okay, and this decomposition is always true. I will write another version. For example, I can say PC, right? PC times PB given C times PA given AC, BC, right? This is also true. Okay, this is also true. And here I want to give you a quick recipe, very easy. And it's quite useful if you are writing a paper or do a paper review. It's very easy to see whether some equation is correct or not. Is this basically requires some balance between the left side and right side of your equal mark. So let's say we have a P, A, B, C, D, and we want a full decomposition of this joint distribution. And what we can do, firstly, you just take out whatever random variable you like, right? Let's say you take out this D, okay? Take this out. And then we can use this one to multiply with another random variable. But this another variable should be chosen from the rest of the options, right? Let's say we take out the B, and then after this bar, this pipe sign, you need to write out all the variables appeared on the left side of this bar. Now on the left side of this bar, you have a D, okay? Then it's an N, okay? Then you time more variables, let's say C. You have BD before this pipe, then you take out BD on the right, and then multiply with A given BCD, okay? So this balancing around this bar or this pipe is very easy to get. So consider this as a recipe, and you can use this trick to decompose any kind of joint distribution without considering any conditional probability, without any conditional probabilities. Right? This is always true, right? So if you want to form up some joint distribution, you can first write out a decomposition, for example, like this one, and then you infer different components, right? Then you infer different components. For example, you can simplify some of the components, or you can assume some of the components are Gaussian, or some of them are beta distribution, etc. Right? You can do this kind of assumptions. And this is very powerful too. Later during this semester, you will see it's quite useful. Okay, so for the decomposition. And another thing, also too, we leave the question 3 later. This is a mathematical game. We leave that later. Let's go back to the lecture first. Okay. We discussed the causal and diagnostic reasoning. If you have any question, please let me know. Otherwise, we will go on. Any questions? No. Okay, good. So once we have this equation, then the solution is easy, right? You see, we decompose that as a Bayesian equation or total probability, and then this guy can be decomposed as the marginalization over open, right? This is a marginalization over open. And then you have the complete equation. So you plug in these assumptions. Like PZ given open, you may get this value from experiment or calibration, okay? Then the PZ given not open is also assumption, which is 0.3. So who can explain if you add this two up, it's not 1, right? Why that? Why that is not 1? Why is not 1? It seems that the probability should sum up to 1, right? But these two, they're not summing up to 1. Can you explain why? Who wants to say something? Can you raise your hand? Or you just click the yes button if you want. Hello, hello. Okay, PZ is not 1. Yan Xu, can you further elaborate your comments? Unnormalized, no, not normalized, no. PZ not open plus open is 1. Yeah, San Hun Jong, you are right, right? You are right. This is continuous. Okay, you have many good comments, right? Many good comments. But actually, students San Hyun Jung and Song Chang Hao, you get the point. Okay. We should know that when we talk about this probability, what is a probability? A probability is you have a set of events may happen, right? And you consider experiments. The experiment will turn out with different results. Right? The probability is if you add up these different results, you will finally have a probability equal to 1. Okay, then each percentage of this probability is just the likelihood that you may observe some of the output. Okay, so of course these two, P or Z given open and P Z given not open, they're not what? They're not belonging to the same experiment, right? They're not based on the same conditions, right? Your condition is what? The first guy is open, the second one is not open, right? Not the same condition. They're not from the same experiment. So what is true then? What is true is the PZ given open plus the P not Z given open, right? This should be 1.0, okay? This should be 1.0 and not the other one, right? Not this one, right? This one will not give you 1.0 because they're not from the same context. Okay, very good. Very good. And then, so with this assumption, you can see that if the door is open, I will observe Z, which is 0.6, and I close the door, right? The door is not open, the probability of observe Z is 0.3. What does it tell? Right? It tells that when you see the Z, you have a higher probability that the door may be open, right? Intuitively, that's the case. Right? Intuitively, this is the case. But we can see, we can prove that. We can prove that this is exactly the case. And these two equations is like what? These are the sensor characteristics. Maybe I spell wrong. I spell wrong. Only characteristics. That means if I use the sensor Z, what should I expect, right? You will have these values from where? From your sensor's menu, right? From the menu of the sensor. So they should do this before they send the sensor to you, send the sensor to customer. So that's the characteristic of a sensor. That can be done by a calibration or by a specific experiment. And another thing is, this is called what? This is called the likelihood. Okay. This is called the likelihood. Another thing is this guy, right? This is prior. That means typically, will this door you're observing, is that open or not, right? If you have nothing to say, then probably it's half. Yeah, half the probability. Okay, half of the probability. Good. Then we can plug in the values, and we can see that the P open given Z is if you see the sensor reading is Z, will the door be opened with a fancy equation, and then you finally get this value, right? This is the result, right? 2 out of 3, 0.667. That means Z raises the probability, right? Z raises. Again, this Z is what? It's the value of the sensor reading, right? I'm keep repeating this because I want to make sure that when you see the lowercase letter, it's the value, right? It's not the sensor, it's the value. If you see that value, it raises the probability that the door is open. Okay, this is the probability that the door is open. Why that? Because previously your prior is 0.5 and now it's 0.67. Okay, that means what? Sensors, they're really helping for this data estimation. And now it comes another problem, right? How can we combine the evidence? Right? You have a very good evidence, which is the Z. Now we rewrite the Z as Z1, okay? As Z1. Probably we have, supposedly we have another observation Z2, okay? What does it mean? It means we have a sensor, two sensors on the robot, right? One is Z1, the other is Z2. Maybe Z1 is a camera, Z2 is a LiDAR, right? They're made from different natures of the anyone saying something? Or? No. Okay, good. It's from different natures of the sensor. Okay, you have two sensors now. Okay, previously you only have one sensor. Now you have two. Then what will happen? Okay, how could we integrate this information? That means Z2, right? Previously we know about the equation of Z1. Now we want to add the Z2 back to the experiment. Okay, now the problem becomes I want to compute the P open given Z1 and Z2. Okay, Z1 and Z2. Okay, from the review lecture last week, we know that we understand Z1 as what? This is the background, background knowledge. If you know this is the background knowledge, then what? You can ignore that first. Ignore this for a moment. Right? We typically write out what is the equation to compute P open given Z2, right? Because Z1 is the background knowledge. Then we add back this background to each of these components to the right side of the bar, right? You have bar, and then on the right side of the bar, you add back all these Z1, and then you will have what? You will have a complete equation for the. This is what? This is also a diagnostic reasoning, right? Okay. Good. In this process, you can see. How about this one? What is this? What is this part? This part is P open given Z. This is the diagnostic reasoning by knowing only Z1. Where is it? This is from the previous page, right? You already know that, right? It's this part, right? From the previous page. It's a P open given Z. It's a P open given Z1. We know this already. And how about this one? The PZ2 given Z1. It seems this can be a quite complex problem, right? I want to see what's the conditional relation between the two sensors. You can say maybe the relationship between these two sensors, they're not related, right? They can be conditionally independent given some states. Then this is the conditional independent. Then the value on Z1 you see from Z1 is not dependent on Z2. Okay, you can use some assumptions like that, right? But typically, this is what? Again, that's only evidence, right? As this evidence, that will be the same for all the cases, like what we discussed in the here, right? Like what we discussed here. Okay, evidence will be the same for all the cases. Then your sensor reading, based on a sensor reading, to infer the state is only related proportional to the joint distribution. Okay, that's a good assumption. So we know this part. This part we can put more assumption, and then what is that? Okay, then what is that? That's nothing else than what? Than causal reasoning of given the open, what's the probability that's of Z2? What's Z2? So we explain that to not expand. We take this out, we can see that if we know the state of the door at time t1, at a certain time, then the measurements Z1 does not give any further information about Z2. Okay? Z1 does not give any further information about Z2. If we draw that on the graph, it seems like if you know the door is opened or not, if that's X, if you know that, and then the Z1 and Z2, they will be a conditional independent. Okay? Then the information cannot pass through, right? Cannot pass through. Information cannot pass through because the information will be stopped by this X. Okay. That means what? That means the probability of Z2 given X and Z1. Actually, you don't need the value of Z1, right? Because you have the value of X already, right? You know the state already. You don't care what other sensors say, right? You don't care what's their readings, right? You only care about the real state of the door. Based on that, you can already have the reading of Z2, okay? And these should be equal, okay? Should be equal. And in the mathematical term, it's exactly the definition of the conditional independence, right? So Z1, Z2, they're conditionally independent. Conditional independent, given the state open. Okay. So now we can plugging back everything, to solve the PZ2 given Z1. This guy. You can do what? You can do the similar to what we did before. So it's a marginalization over open. Okay. If you want to really compute that, right? This is the marginalization over open. So that's PZ2. Given Z1 is nothing else than the PZ2 open given Z1, but we need to sum over all the possible open. Right. The state. That means you have the case of open, you have the case of not open, right? Okay. To consider the case of open, consider the case of not open, you have these equations, okay? And that one serves as a background knowledge, okay? That one serves as a background knowledge. Be more specific. To be more specific, this guy is what? This guy is a PZ2 given open, and Z1, right? Equals to this. We can take out the Z1 because of the conditional independence. So you have the complete equation and plug in all these values. In this, we have the assumption like this, right? These are the sensor features, right? These are all the sensor characteristics. So given the open, Z2 is 0 to 5. That means if I have the door opened, what are the chances to see the value Z2? It's half the time, right? But if I know the door is closed, then the probability to observe Z2 is 0 to 6, right? A little bit higher than the random guess. Right? 0 to 5 is it's like a random guess, okay? I just don't know what happened, right? This 0 to 5. 0 to 6 on this side is a little bit better, a little bit higher probability. And we know this as P open given Z1. We know this already from the previous page. Plug in everything, you will get 0.625. You know, previously it's a 2 out of 3. Right? This guy is 2 out of 3. This is a 0.667, right? That means if I see the value Z2, again, Z2 is a value, right? If I see the value Z2 from the second sensor, you see that value, right? It lowers the probability that the door is open. Then the second sensor, the big Z2, in this case, is more of what? Not an open door detector, it's a closed door detector, right? If you see that Z2, that means the door has more chances to be closed. Right? It's a closed door detector. Z1 is more like an open door detector. Okay, if you see Z1, Z2 at the same time, okay, you have some probability between a random guess and by only observing Z1. Okay. Specifically, it's this number. So the value itself doesn't matter so much, right? It's important to know what is the theory behind it, what is the structure or analysis. Good. Okay, now things getting more interesting if you have more sensors, right? You have more sensors. Maybe on your robots, you see nowadays, like at the very beginning of today's lecture, right? So I showed you a video of autonomous driving car. And this car, you have many LiDAR, right? That car, we have about 4 or 5 LiDAR sensor, LiDAR related sensor. Also, there are 5 cameras, and also 12 ultrasonic, and also MU and the GPS, etc. So you have collections of sensors. A typical robotic system have not only a big number of sensors, also all these sensors are generally they're heterogeneous, right? Heterogeneous means they're not from the same sources. You can have camera, have LiDAR, have different types of sensors. And with a mathematical abstraction, and any sensor reading will be a Z, right? It's nothing else than Z1 to Zn. If this is the case, previously we mentioned that, okay, you have 2 sensors to measure the state of the door. This is simple, right? We can even calculate the joint distribution and find out the probability. And if you have many sensors, then what will happen? Okay, that's the generic form, right? General form of what? Of how could you combine this evidence, right? How could you combine all this evidence? And we have what? We have some assumptions so that we can simplify this problem. This is our previous plot. This is our previous problem. And we had Z1 and Z2. And now you're telling me what? You're telling me you have not only Z1, Z2, Z3, up to Zn, okay? So the graph just looks like this. You have one state, you want to, you have a state, okay? You have a state X, and then you have many sensors. How can we find the state given all your sensor readings, right? Z1 up to Zn. Okay. Now this is an important question. How can we find that? Right? How can we find that? So we need a way to combine this sensor reading, that means sensor fusion. Okay. Let's take out one of the sensor reading, for example, Zn. We take out Zn, we can change this the left side, that's the diagnostic reasoning, to this causal reasoning. I want to know about the characteristic of this sensor, right? If you have the state X, what's the distribution? What's the distribution of this Zn? Why we care about the state x? Because this is a problem we want to solve, right? We want to know the probability that the state is x. Again, lowercase is the value, right? I want to know the probability the system is at this state x, small x, given these sensor readings. Okay, and then just following the previous equation, you can see we kick out that n given x, and then I should multiply with a prior, right? On the right side, that's the prior. On the left side, that's the likelihood, right? This is the likelihood. What is trivial is this part, right? It's only about the relation between the sensor readings. Right? That will be the same no matter how you choose the x. Okay, if you choose a different x, you want to find the probability whether, let's say that's maybe the road location, if the position is at 1.0 meter or 0.8 meter, no matter what, no matter which value, it won't change this evidence, right? Then we do what? We use a normalizer, we use a symbol to represent the normalization of the joint distribution, right? Let's take that as a normalizer. And in this case, we only have the joint distribution. Only have the joint distribution. The next step is what? And you can see the green part, they're actually the same format, right? Same format. Now, how do we solve this guy? How do we solve the part on the right side? Again, you take out one random variable, for example, z minus 1, and we want to find the pz minus 1 given x times the rest, right? We follow exactly the same definition. So if we have a Markov assumption, that means all the z, they are conditionally independent given the state x. If this is your assumption, this is the Markov for that, because we are talking about given this x, what you observe in, for example, Zn will have nothing to do with the rest of the sensors. Okay? That means the information generated by any of these sensors, for example, some information can be seen from Z1. Z1 will provide some information. I want to pass this information to all my neighbors or to the system so that everybody knows Z1 sensor have observation Z1, right? I want to pass this information out. But when I use this information to infer this X, then this information will not be further passed to other sensors, right? Because every other sensor thinks if I know about X, I don't need any help from Z1. Okay? I don't need any help from Z1. So the readings of Z2 or Z3 up to Zn is independent of Z1 given the state, right? Given the state X. Okay. Previously, we consider maybe Z1 in this case subjectively, right? Consider this as a person. I want to pass this information to the whole system, but the information will jump. Let's say the first step is to the X, and then I want to pass this information further to Zn. Okay, and Zn said I don't need it because knowing X is good enough. So this is what? This is a Markov, right? This is a Markov assumption because you only need the one-step information, right? You only need the one-step information. Later we will give more example, but most of you know about this already, right? So with this Markov assumption, all the following analysis is about how can we further stack these products, right? Stack on this product. So you have a P of Zi given X. So it's a P Z1 and P Z2 given X, P Z3 given X, whatever. And finally, times is the px and having a product. Okay, having product. Then you what? Then you have the joint distribution, right? It's nothing else than a joint distribution. You can also see that from this plot, right? You only have nothing else than Z1, Z2, and Z3. So you have the P of X, that's taking out the origin of your joint distribution. And then what? Then you take out every pairs of this joint distribution, right? So for the first pair is just the P of X, Z1. The second pair is the P of X, Z2. Right? The third one is the P of X and Z3. And we know this joint distribution is proportional to this diagnostic reasoning, right? Okay, and finally you get a series of products. Okay, you get a series of products. That's the equation you get here. Okay, and you can see it's just a recursive solution. This is also known as what? You can give me the term. This is also known as naive Bayesian, right? Naive Bayesian. If you use that, if X is a discrete, if X is a discrete, for example, a label, if that's a label, it's a naive Bayes classifier, right? Classifier. Okay. Like how can we recognize object is a human, for example? If that's a human, probably you see the head, you see the leg, you see different features, right? These features, they are independent. So given this feature, that confirm my assumption that this X, the capital X random variable, that's a human, okay? If it's a labeling problem, a classification problem. And in this case, that's called a naive Bayesian classifier. The general form is that we have the Markov assumptions on all observations given the states, and then that directly lead to naive Bayesian. Okay. Okay, that's some extended material. So by knowing this, you can see that's how we manage the different sensor data. How we manage the different sensor data. How can we do the sensor fusion? Okay, that's how do we do the sensor fusion. Later, I don't know whether we will do that. Hopefully we can do that. For example, everybody know about EKF, right? Common filter or other UKF. So if you explain EKF or UKF, the common filter like sensor fusion, this is what? This is just loosely coupled. This is nothing else than loosely coupled state estimation, right? I get the result from every aspect, and finally I use a product. Is a product of the probability, so that I have a loosely coupled state estimation. Okay, because based on some hints that 1 up to that n, I can predict the state, and finally the overall state. This overall state based on each sensor or each information source. I can use any of these to predict the state, right? Finally, it's nothing else than a product of the separate information, right? So that's also the theoretical basis for the common filter, right? Also the theoretical basis for common filter. In this course, we try to unify all these concepts because finally you can see Bayesian is a very powerful tool. Okay, this part is only about the observation. Okay. Have any questions? Do you have any questions? If no question, let's move on. Okay, let's move on. So now you know the states. Okay, now you know the states. How about we combine the sensing with some action, right? Combine the sensing with some action. Mobile robots or robot arms or these UAV, it doesn't matter. So finally, you need some execution of task, right? You need some actions. We want to combine the sensing and action together, right? Only by sensing is observer. For robots, it's different than a game, right? Because you finally need to act. You need to act on the real world. So how can we combine these actions, right? Acting with the sensing? So this is the second topic we will discuss today. Now we know the robot senses the door state by sensor fusion, right? You have many sensors, and we can allow it to open or to close the door. Okay. So previously we only have a camera, and now we have the robot arm, right? So previously you only have a sensor, now you have a robot arm. This robot arm can operate the store. It's brought. Okay, then what's real action result? What's the action real result? So action is modeled at the random variable u. At random variable u, you can imagine that for the mobile robots or autonomous driving vehicle, this u will be what? This u is the control you generated and apply to the robot system, right? It can be some velocity or rotation, also what? Or sometimes you can consider this u is nothing else than odometry, right? Okay, later we can reuse this concept. So far, come back to the door opening problem. We have a random variable u, where in our case is a capital U is a small u. This is important, right? We want to use this guy. This is what? This is a value, right? It's a specific, quite specific action. Just a specific action, right? We take this u. This action means I want to close the door. Okay. This overall random variable is a capital U. Probably this is a set of actions you can take. Okay. We choose one specific action is called U, which means to close the door. Okay. And when you apply this action, you have possibilities that it may fail, right? It may fail, and sometimes it will succeed. Right? And it depends on what? Depends on the previous state of the door. If the door previously is opened, then this action, small u, this action, small u, will succeed in 90% of all cases. Right? Succeed in 90% of all cases. And when we put that into a state machine, that means I apply u, it will result these complete graph. Okay. If it's previous open, you have 1% of a chance. It's still open, right? Still open because it's not working. Okay, U is not functioning. You have some failure cases, and then another 90% of chance the door will be successfully closed. Right? If previously the door is closed, when you apply U, at least you don't have a counter effect, right? So it will keep closed, right? You don't have a chance to forcibly open the door by applying U. Okay, if this is action, then the key question is what? The key question is the outcome of the action. For example, this guy, Px given U, how can you compute this one, right? Given the action U, we want to know the probability that's the P of X given U. How do you do that? How do you do that? We know that you have sensors on a robot. These sensors on the robot will help you to determine the state. okay, determining the states. But for now, we separate the problem a bit, right? We first look at if you have a u, then what will happen on this x. We do this by integral over all the possible previous states, x prime. Okay, if previously this x is open, and then that's one case for your calculation. If previously it's closed, that's another set of calculation. Okay, this is what this is called a total probability, right? Total probability is a marginalization over x. Okay, marginalization over the previous state x prime. Okay, by doing so, this x will be marginalized out. And you can look at this equation. This equation is quite nice, and it's quite balanced, right? So you have px given u is a marginalization. We marginalize out this x prime, so we cancel out all this x prime. Then you left px given u, right? So it's quite a balance, right? So you won't make mistakes if you write out this this equation. And also you have a continuous version. This version is a px given u is the integral over this case of x prime. Okay, by taking out all the x prime and this integral, you will get the px given u. So our equation is quite balanced, so we don't explain further, and it's very easy to track this definition. Good. So how can we do the computation, right? The P open given U is marginalization over the previous state. The previous state can be P open prime, can be P not open prime. Okay, under each case, we want to give these action probability, right? That's the result of U. Okay, this is the result of U. If we extend that to, for example, a mobile robot problem, right? You have the P of X given, sorry, XT, given your control at T and based on the previous state, right? If previously the robot is here, and apply a control U, and finally it will arrive maybe like a Gaussian distribution here as XT. This is exactly this guy. Okay, that's a distribution. Okay, this is the distribution. The distribution of xt given the u and the previous state. Okay, previous state. So we want to summarize of all the previous x prime. When you summarize all the previous xt minus 1, we can use that to infer the current state. Then we plug in all these probabilities, right? Plug in all these probabilities. You have this from the graph. You have that these two from as a prior or from the sensor reading, right? From sensor reading, and finally you get this probability. Okay, and this guy, second one is P not open given U. It's very easy to get, right? Because your experiment is to apply this U. So under this condition, the P not open is simply 1 minus the P open given U. Okay, this is a 0.9375. So in summary, the P open given U is very low, right? It's around 6% of chance, 6% of chance. So, any questions so far? No. If you have a question, please write to the chat window. Right? Write to the chat window. Okay, so far we learned these two ways to infer the system state. Okay, infer the system state. One is called sensor update. Right? Sensor update. We draw that on the what's it called? I forget what's it called. This one. What's the name of this app? Notability. Okay. We draw that on notability. That's this guy is this one, right? You have Z1, probably also Z2, etc. This is a sensor update. Okay. The second one is you have a U, and you want to use this U to change the state of X. Just note the directions of its arrow, right? Note this arrow directions. This is important. Okay. Sensor update means I want to do what? I want to have some sensor reading based on these sensor readings to infer the current states. But the action update is I have some action can directly affect the state. Okay, that's why this arrow, the directions are different. Okay, your U can directly control the state, direct effect on the state, but the Z will not affect on the state, but it is a reverse, right? Your state will determine the Z, right? X will determine the Z. So that's why all the arrows will start from the X to Z, but they will start from U to X. Okay. Now we can combine both. Right? We can combine both. We can define that if this is your state space, and that will be a sequence of sensor measurement and actions until time t. So you can see you have U1, Z1, and U2, Z2, up to UT, ZT. We have some control to the state of the door. You have some observations, and then up to time t, right? This is the process. Then the belief is what? Belief is how much you have the confidence, right? It's a belief. Belief is also a posterior. Right? When we talk about belief, the belief should be a posterior. Based on your previous prior and what you observe now, which is the likelihood, that gives you the belief. Right? So finally, it's a posterior. Of the current state xt, defined as the belief of xt is the diagnostic reasoning, right? Is the posterior pxt given all your previous controls and previous observations. This is clear, right? This is clear. And this equation can be quite complex, as you can imagine. So maybe I have been doing this experiment over a year. Right? So I recalled all the previous control and all the previous states originated from this X. And finally, I want to know what? I want to know the present state, xt. Okay, based on all my previous history knowledge, I want to infer the probability distribution of the current xt. Again, this xt is not the random variable, this is the value, right? I want to know the distribution of, if I choose the small xt as my target analysis objective, and then the probability distribution of xt given all my previous observation and control. Okay. So what is important is at the present time t. And that's known as a belief. Right? So you have belief xt is the probability of xt given u, z, etc. That's what? That's a combination of a time series, combination of the time series of the it's assembly of the time series of knowledge. Okay, this is known as a dynamic Bayes network. Okay, dynamic Bayes network. If we separate that, you can see that's the control to the robot. This is the observations. That's the state. Okay, a long time, right? But everything started with x0, x0, and you have z0, you have u0. Okay. This structure, maybe it reminds some of the students. This structure looks like what? looks like a, but looks quite like an RNN network, right? Like an RNN network. Because it uses the previous state to update the current state. That means if you have the previous output, you can use that as the previous condition, right? Xt minus 1 will be a condition to xt. And I have input u and output z, right? This structure can be understood similarly as an RNN network, but physically they are not the same, right? Physically not the same. So we're not talking about the data input and data output. It's a little bit more complex than that, right? A little bit more complex. They are physically, you have some control variable, right? You have motors, you have the electric boards, so they will perform this execution or some motion, right? This is the U. And this U will affect the current state. And the current states will lead to different observations Z. Okay? Also, you can use this dynamic Bayesian network to analyze the effective or RNN network as well. So if you want, but that won't be the topic of today. Okay, let's have a quick rest. We restart at 7:30. Okay, restart at 7:30. Then we discuss how these equations can be deducted and what's the final findings. 7:30. Okay. This one. Okay. Can you hear me now? Can you hear me? If you can hear, can you raise your hand? Okay. Yes. Okay. Okay. Nice. Nice. Okay. Let's continue. Yeah. I talked a bit, but my computer was muted, so I need to reintroduce. So we were here. Okay. We have an overall process. The process is called a dynamic Bayes network. This is a dynamic Bayes network. You need to track the states, and you have some control, and you have some sensor reading as observations. Let's grant some physical definition. Right? So it's like you are tracking the motion of robots, right? Because we will use this example in the future as well, right? That's where the robot mobile robot was at xt minus 1. And then after you add some control of ut minus 1, the robots will move to a new position. This new position is xt. And then along time, the robots will move again based on the control of ut. Based on the control of ut plus 1, then ut plus 1 and this xt will determine the new position xt plus 1. Okay, so that means these two guys will determine this one. Okay, and these two will determine this xt plus 1. Okay, I may have made some mistake in the explanation, but this one is true, right? So based on the previous states and the control you granted, then finally you have update to xt. Okay, that's the case, and we incorporate our Markov assumptions. This Markov assumptions happens along the directions of these arrows. Okay, first one is the P of ZT, you already know this, right? P of ZT given this guy, P of ZT, given all these X, all the U's, and all the Z, that means what? Given ZT and all the rest, right? Sorry, this one, this should be T plus 1 or something, right? So basically, what is important is ZT is not dependent on any of these given xt, right? Given xt, given xt. That means the only information source of ZT is xt. Okay, that's one Markov assumption, because any information you need to jump more than one step will be ignored. Right? Will be ignored. So it's Markov. Okay? Xt is the basis to analyze ZT. This is for the measure. And secondly is the state, right? The state. You want to infer the state xt based on the rest of the world, and we only care about this xt minus 1 and ut. Okay? Then we don't care about all this. Right? We don't care about all this. We only care about this red area. Okay, this is another assumption. We call this measurement update. This is the state update. Okay. Then finally, we want to see overall what's the problem we're interested in. I'll copy the complete graph here. You can see the graph now. So, what is the question? What's the key question? What's the key question we want to solve? The key question we want to solve is about the state. Right? You can solve other problems, right? But what we want to solve is our belief on xt. Okay? The belief on xt. That means this one. But this one is a key problem we want to solve. What is the belief? The belief we previously mentioned is a posterior on xt given what? Given the rest of the world. For the moment, we can ignore. Let's first ignore everything happens in the future. Right? Let's first ignore the things happen in the future. So the belief for xt is the p of xt given what? Given everything you have observed in the past, right? Observed in the past. So that means you have the u's, all the u's, and all the z. All the u's and all the z as a vector. It is u and z, they will range from time 1 to time t. Okay, and time t. Let me rewrite that. Okay, this is the belief we will want to solve. So how can we solve this problem? And we know this is that means taking. I choose another color. This part is what you have done before as your control. Your control U and all your observations, right? Or the control and observations. So that's these parts. Okay. Why we are not taking into account this xt minus 1 for now? Because we don't know that. We don't know it. The only condition we have is I can record what did I observe, what I have observed so far, and what control command I have sent to the system. So that's the only thing you know. Okay, that's the only thing you know. I want to use that to infer this xt. And this problem can be solved by what? This is a diagnostic reasoning, so we can change that to a causal reasoning. This causal reasoning is P of, but we can take out one likelihood, right? How about we look at the relation between xt and zt? Right? We can take out this guy, and then we have zt given xt. Right? We take out this xt, and then we need to swap the two sides, right? It's like you have p x given o is a p o given x times px, right? Proportional to this. So zt, take it out, and then you have xt on the right. Then we copy all the rest, right? We have u1 to t and z1 to t minus 1. And this part is the background knowledge. There's nothing else in the background knowledge, so you directly copy that, right? And then times what? Times p of xt, right? P of xt. So you have p of xt. You need to copy the background knowledge, right? So you have u1 to t and z1 to t and z. Sorry, you don't have a z. Okay, t minus 1. T minus 1. That's all you have, right? That's all you have. And then if this is the case, we have Markov assumptions, right? So the PZT given XT, that means knowing the robot position, or the states, what you observe, that's what you observe given the states, then the rest can be removed, right? Can be taken out. So you have the P of the T given the XT. Right? This part, we call that, we take use of the Markov. Make use of Markov. And then times the P of XT given U1 to T and Z1 to T minus 1. Okay. This should not be equal sign, so we use a normalizer, right? We can add them for the normalizer. Good. Then you have Markov. So based on this Markov assumption, so that's something more like what? This is the sensor model, right? Given the robot location, you tell me what you should see, right? What the sensor should see. Condition like in a 1D world, if you have some LiDAR sensor can measure the distance to a wall, then if you already know the robot position, you should know about the distribution of the LiDAR readings, right? So that's a sensor model. Okay, this is a sensor model. How about this one? This one seems quite weird, right? This is quite weird because I want to know how can I get the value xt, how can I get this value t based on the previous observations and the control. Okay, previous observations and control. That means I want to, based on these and these, to know what? To know about xt. Right? To know about xt. Okay, so we can see that you have no idea about this xt minus 1 yet, right? So you cannot take out this zt minus 1. Because what? Because xt is, you have two sources, right? One is a ut, the other is a previous state. Okay, only by ut you will not know, you have no knowledge about xt. So similar to what we discussed just now, if you have a robot's previous position is here, and we grant a control ut. So finally, the robot arrived to a new location, but with some uncertainties, right? That's the distribution of pxt given the ut. Okay, so you should know xt minus 1. Otherwise, you cannot know this pxt, because when you perform the control ut, you don't know where you started, right? You don't know where did you start it. So actually, it's not only ut, it's ut and xt minus 1, right? You cannot lose with xt minus 1. But we don't have the term of xt minus 1 yet. So we need what? We need to use the total probability, right? So use the total probability, or you call that a marginalization, marginalize over xt minus 1. Okay, what you will have? You have the normalizer times your sensor model times what? Times a marginalization over xt minus 1, right? You have marginalization over x minus 1, xt minus 1, xt minus 1. How can you marginalize all that? That means we need to add the term of pxt minus 1, right? Given your background knowledge. Given your background knowledge. Just write BG, right? Given your background knowledge. And also what? You also have the pxt given xt minus 1 and ut. You have something else, but you don't care about this something else, right? Because of the Markov assumption. Right? If you know about ut and know about xt minus 1, you're good about xt already, right? You don't care about the rest. So this is also Markov assumption. Okay. Once you have that, you see everything is clear, right? Everything is clear now. Previously, I want to compute the belief of xt. Now I have what? I have the eta p zt given xt sensor model times the update of my action times what? Times the belief of xt minus 1, right? That's all. Okay. This equation is finally it's become iterative again, right? Become iterative again because we can use the state. We can use the information at t minus 1 this belief to compute the new belief. Okay, to compute the new belief. That can also be seen on the graph, right? If you know about xt minus 2, you can use that to compute the xt minus 1 with the help of ut minus 1, and you can further involve, right? You can further involve. So on the right side, it's like previously it's xt minus 1. When I grant ut, you get this distribution. And if you know about the distribution at t minus 1, and you apply a ut plus 1, you will get a new distribution where it is as the pxt plus 1, the new time, and the previous xt, and then the ut plus 1. Okay? So now everything starts to make sense, right? We have the full analysis on how could you do the inference by given the control and all your sensor readings to a state estimation, right? To a state estimation. Good. Any question? That's the question. No or X. No or X. I don't know what you're referring to. No or X. Punctual Hey, on mute. You can speak now. Hello. Okay. Okay. Good. Okay. Now we can continue, right? We do some mathematical deduction, but seems quite easy, right? We have nothing else than analyze on this graph. Right? This graph is just said if you have your previous states, some control, some observation, it's good enough to know about how the system will evolve along time. Right? How the system will evolve along time. This is called the dynamic Bayes equation. And the deduction should be correct. I didn't check, but it should be correct. So you can verify that by this page. So this belief now seems still complex, right? Still quite complex. If I want to know about the current state xt, I need to know the previous state xt minus 1. How do I know xt minus 1? I should know about xt minus 2. Then that should based on t minus 3. Finally, it's back to the origin of x0, right? And every time you should do what? This is similar to a convolution, right? You need to convolve. So finally, we will analyze this equation in another lecture. Okay. So this algorithm, general algorithm, how can we use the Bayes filter to get the belief? We can get the belief of x by a d, right? A d. What is d? If d is a sensor measurement z, and then you do what? You do a Bayes equation, right? The Bayes equation, because the previous prior belief, the prior, this is the previous prior, multiplied by likelihood, right? This is likelihood. Okay, clear? Prior times likelihood is proportional to the posterior, right? Posterior will give you the new belief. Okay, this is the posterior. Okay, this is clear. Good, very nice. And then you need to add this to the normalizer, right? Add this back to the normalizer, otherwise it's not totally proportional to original evidence. So this is added as a new evidence. Then for all the x, we should do a update like the total probability, right? Total probability. So if D is an action, that means I can directly control the x. We should do what? So we should have a total probability to marginalize out of all the previous states, possible previous states, x prime. Then we directly return this belief of x prime. Okay. So this is a Bayes filter, and that can be applied not only to robotic applications, can basically apply to any process, right? Because you see, we simply said sorry, we only use the P, right? Belief and B, L, and P. We not specify, non-specify, right? We didn't specify this should be a Gaussian or should be anything else. So if you have a process, this process will, let's say, interdependent, right? If a dependence, the current state depends on previous states, this should work. Okay. And there are many variants of this Bayes filter variant. For example, a common filter, a particle filter, a hidden Markov model, networks, a POMDP. So all these can be modeled as the Bayes dynamic Bayes filter. Okay, a summary to this lecture. You have model-based, we introduce model-based agents. We maintain an internal representation of their environment. So typically we call these either a state or map, if you have such a model. And they are capable of localizing themselves in environments by filtering technique, such as this Bayes filter. And we apply the Bayesian probability theory. You should see the difference between the Bayesian and the frequentism, right? Bayesianism and frequentism. And we use the Markov assumption to recursively estimate the state from observation and action. So it's a statistical filter. It estimates the distribution over random states and observation actions. So this is the summary. This is the summary. Okay, we have various variations of methods. Here I give you an exercise. You can download this exercise online, and this is not mandatory. Not mandatory. That means you can choose to do it. But I will release the solution next week. I will release the solution next week. Good. This is lecture 2, and if we go back to the lecture questions, and I use this to you can call this as a summary of the Bayes network, or you can call that a summary of Markov process. Right? We talk about a magic. It's a magic game. How to say? So firstly, I generate a series of numbers. This series of numbers are random, right? 3, 4, 2, 5, 3, 6. Basically, it's a long sequence of after this 6, that's the 4. Right? Okay, after the 6 is the 4. So it's just a random sequence of number. Firstly, I want to ensure this is random generated. Or if you want, you can write your own version on your paper. Just randomly choose some number, okay? And there is a special rule. When you apply this rule, you will see magically, when you count these numbers, you will count to these 4 or this specific 6. What's the rule? The rule is you can start with any number you like, right? Let's say I choose this one, right? This is number 2. If I see a 2, I will move 2 steps forward. I arrive at a 3, then I move 3 steps forward. I have 8, 4, 5, 6, 7, 8. I will get this 2, 1, 2. I will get this 8. I will get this 3, 1, 2, 3. This one. This one, 2, 4, 3, 3, 7. 1, 2, 3, 4, 5, 6, 7, 3. Now you arrive to this 4, right? If you miss this 4, you will continue, and finally you will arrive to this 6. This is always the case, no matter where do you choose the start point. You can start with the 3, you can start with this 1, or you choose start with this 5. Just choose any initial number at the beginning of the sequence. Okay? And when we play this game on the platform, usually we show that as a card game, right? It is a card game. You just take a deck of cards, and then you reshuffle the deck of cards, and you can let the inspector to choose any one of the cards at the beginning of the deck, and when you count, then you count the numbers of cards shown on the specific card, and finally you will review one of the cards, which will be the falsely chosen card, right? Will be this 4 or the 6. And that's the complete game, right? You can try that out, right? By taking out any number, probably, okay, let's start with this one. And finally, you'll see it will arrive to this 4. Otherwise, it will arrive to the 6. So these are the rules, right? Can you use the Bayesian process to explain why this magic can work? Okay, you just choose a random start point and you count the numbers. If you arrive to 3, you count 3 numbers. Right? You arrive to a new number, then you count this number of positions, and finally you arrive to this 4. If you don't arrive to this 4, you arrive to this 6. So why that? right? Why that? Why could this game work? So you can explain that with the Bayesian. It's a Bayesian process. You can track the states and then see what you observe, etc. But I need a more complete explanation, right? Why this game can work. So can anyone show some idea? Can you click the yes button or raise your hand to show your understanding? Okay, there is Z John DQ. Yeah, I don't know if you have your full name. Zhang Zheng. Yeah, I already unmute you. Yeah, yeah, you can speak.
So I think it is because, can you hear me?
Yeah, we can hear. Yeah.
I think it is because you back to the you look back all the previous 10 numbers and all this will give to either 4 or 6 because for example, if you look at the 4, the black 4, the previous 3 numbers will either give will all gives to 4 and
yeah.
all.
So this tractor I put here, you can consider this is some setup, but typically you don't need this setup, right? You don't need that setup. The complete game is you can use a random number generator, and finally, if you track some of these games, some of the chains, let's say you randomly choose 2 or 3 or something, and then you just choose a number which is far enough, right? Maybe I choose a number when I stop at the 20th of the game, the number 10th of the game, and finally you will see a number, right? You just directly pick that number. You don't need to test it. You don't need to test that by the first, second, third. You don't need to really test that over the first 10 numbers. You just choose any one, and you follow this rule. And finally, probably you will choose that, okay, that will arrive here. And then whatever number you choose, before that, right? Probably I take this one, right? I take this 7, I will take this 4. Doesn't matter, right? Finally, following this rule, it will always fall into these specific bits. That's where this magic happens, right? You don't need to do the statistic like I need to test what will happen if I start with any of the first 10 number, and finally they will contract to 4. You don't need to do that, right? I will just pick one and I make this again, like for the first step, second step, after 10 steps, after 20 steps, finally I will arrive to a number, right? I just pick this number. Once I pick this number, then whichever number you pick as the beginning, they will be following this rule. They will finally form this chosen number. Okay. You can do the experiment because when I write out this number, except for these guys, there's some added setup number, but it's only for the effect of the contraction, but really not specific on that. For example, I can take, for example, this 5, right? This 5. When you arrive on this 5, let me show in yellow. So you just pick one pick one number at the beginning, and finally you can see it's higher chance to arrive to this 5. I'm not guaranteeing 100% of a chance, right? But it's very highly likely, right? Highly likely. I will not guarantee 100%, right? I'm saying highly likely you will arrive to this 5. The further you go, let's say the future, further you go to the later phase, then you get a higher chance, higher probability. Okay, I don't know whether I'm clear enough. These or these. Next time you can also play this with a deck of cards. Right? Just reshuffle the card, and you follow the choice of the first card. Let's say the JQK. You consider that as a specific number. Let's say consider JQK as 10. Maybe 10 is too much. Right? And then if you arrive on a 5, then you throw out 5 cards, then you see what's the next number, and then you go through that process, and finally you will see you have a falsely determined cards. It's like what we show here. You just pick a random number. Finally, you will see, okay, I play this for 10 times or 12 times. I will arrive to a certain number. Then I just change to a different starting point, and finally we will also arrive to this number. Okay, this is the game about. Who else want to explain that? Who else want to quickly explain? Okay, then I will quickly try to summarize the reasons why this kind of game can always work, right? Firstly, we know there are certain properties of this game, right? Firstly, this is a Markov. Right? This is a Markov because your next state is only determined on the previous number, right? This is a Markov. So, and also this is the Markov process, right? Because all your P of xt given the xt minus 1, this rule is fixed, right? This rule is fixed. So this is the Markov process. Okay, this is the first thing. And secondly, let's say even if you have the choice which will not fall in onto this 4, right, at the beginning, right? Even if this choice is not on this Markov process, then what will happen? You may launch to a different process, right? You may launch to a different process. Then what's the probability? What's the probability? The probability is okay, if I want to quickly evaluate that maybe over the first 20 number or something, right? First 20 number. And then you have the chance of 1 out of 20 falling onto this Markov chain. Then what's the probability that it will not falling on this Markov chain is 1 minus 1 over 20, right? That's not on this chain. Okay, that means it's like you're choosing a random number. Okay, the next time when you jump to, let's say, if it's not on the chain, for example, jump to this one, again, it's like you're choosing another possibility of not on this Markov chain, right? Not on this chain, so the probability becomes what? 1 minus 1 over 20 squared, right? That's the probability you are not on this chain. So finally, after several steps, you get 1 minus 1 over 20 over n, right? N is the number of steps you will play. So the probability that you're not on this specific Markov chain will be very small. Due to what? Due to this power, right? To this power. Good. That means it's like you start, you have a specific Markov chain. You want the state to follow this process, right? Follow this process, and you can start with anywhere else, right? But finally, they will converge. All these will converge to this dedicated green Markov process. Okay, and this Markov process, after the specific point, then the rules are the fixed. So finally, they will arrive to this form. Okay, arrive to this form. Basically, this form. Okay, if it doesn't work, then probably you have even longer chain. This longer chain will go to this number 6, right? Okay. So this is a mathematical explanation, right? Because once you choose anything randomly, and if it's not falling on this chain, that means just choose a different starting point. Right? Everything is random. You're not on this chain. Then the probability that you're not on this chain is 1 minus 1 out of the samples you want to deal with. Right? If I want to make it work over the first 20 number, then this is the probability that you're not on that dedicated, the selected Markov process. And the second time, that's the probability, right? After nth time, this number will be very small, right? This is the probability that you're not on this chain. This probability is small, that means you have a high probability you're hitting on this predefined Markov process. Okay, that's why this kind of game will highly likely to work, right? Highly likely to work. So if you want to play that, you can set up a random generator. You can try this. You can try this. Question. So even I move the Markov process to another place in the row, I will still arrive at the points. Yeah, exactly. Yeah. If you move if you choose a different starting position, you will always have this arrive at the same point. You can do the test. Right? You can do the test. Okay. Good. Yeah, that's about the general introduction of SLAM, and we have some probability theory. Right? Also, we introduced the dynamic Bayes equation, the dynamic Bayes process. Let me find lecture 3. Okay. Then in this lecture, we will try to continue from the previous model. We have a dynamic model, and then the simplest model you can probably encounter is called HMM, right? Some of you know about HMM already, but from this lecture, you will know we're seeing HMM from different perspective. And also, we introduce the graphical model. Some of the CSE students may know about this already. Consider this as a recap. Some of the ECE students will soon, because when you write a paper, you will see the graphical model is very important. But, okay, let's go on. So from the previous analysis, let's say, for example, this one, right? You see, we just list out so many equations. List out so many equations. But actually, these equations, for example, I can make sure the last one is correct, right? Because of what? Because of we can get many of the assumptions or inference from the graph, from the graph itself. Not necessarily start this algebraic analysis from scratch. And that's the power of the so-called graph model. Right? powered graph model. For the probabilistic reasoning, we want to transform this uncertainty into the probability, right? Uncertainty into probability. That means you have some qualitative measures. You want to have some quantitative numbers, numerical representation, right? And we want to specify the joint probability distribution. And this is the key, right? From the last lecture, you already know, if you have idea of the joint distribution, let's say PABC, you can get whatever you want, right? You can get, for example, these ones, any of these, right? If you know the joint distribution, then you know any of these. So joint distribution is a key, okay? And we want to find the generic form for this inference, right? So that's what is good for the probabilistic reasoning, okay? But besides that, we need to respect another two facts, another two factors. One is the joint probability distribution. This guy, this is very important, but at the same time, it's complex, right? This complexity is very high, right? The complexity is very high. Complexity of this joint distribution. And secondly is we need the independence or the conditional independence for this reasoning, okay? This probabilistic reasoning is powerful, but we need to respect these two facts, right? These two facts is the complexity is high. Secondly, we need the independence conditions, right? Without all this, this complexity is intractable. To understand more, we can see some of these examples. For example, the work done by Daniel Miller from the graph lab. That's quite old demo. I'm sorry, maybe you get some delay in the video. It's basically I'm showing you have UAV can fly all around the complex environments, right? You may encounter some delay in the video, but you can imagine most of you see what is a UAV, right? You have a helicopter can fly around to do fancy things, right? Even you can have some aggressive control, to the UAV. Okay, I will skip the video because it's hard for you to see. Okay, what I want to talk about is if we list out all the states of a UAV. Let's say this is the UAV. In case you don't know, it's unmanned aerial vehicle, right? Unmanned aerial vehicle. And then we can simplify a bit of the problem, right? Like where is the UAV? For the indoor environment, like where it is in X, Y, probably you have X, Y, Z, right? Just you don't need to bother by these details, right? Only want to mention the concept. So you have the positions, and you have the velocities, right? Then you have these rotations. And probably you have other inertial systems and also other parameters, right? Okay, then this is what? This is your state. This is the state, okay? This is the state. And this state can go up to, let's say, a 20th dimension. Okay? If you see some typo error, just don't bother, because probably I should also write a Z here or VZ here, or sorry, a VY here, so it doesn't matter. Right? So finally, the state is you have a 20-dimensional state. What do we need from this 20-dimensional state? You see, from the previous analysis, if we want to update the state of xt based on the xt minus 1 and the ut, Okay, if we want to do such analysis, we need to find what? The joint distribution of all the random variables, right? The joint distribution of all the random variables. What's the joint distribution of all these random variables? How can you describe that? How can you describe that? You need a high dimensional table, right? You need a high dimensional table. So, give you an example. Let's say you have a mobile robot with wheels. Okay, you have this robot. You put this robot into environment. Maybe an indoor environment. There are walls in the middle. Walls in the middle. Something like that. I won't draw completely the graph. And then you want to do a localization problem, right? I want to see where is my current location given all my given all my previous observation and all my previous controls, right? Because I want to localize, right? Localize. Then what is this x? What is this x? You see, this x is a lowercase value, so it must be a value to a random variable, which is a state. Right? State is a random variable for the analysis. So what is x? X can be x, y, and theta. If the two-dimensional robot is moving in this environment, right? So if we show this environment, probably we get a map like that, right? This is the map. So any location in this map will have a coordinate. Okay, that's exactly this x and y. This is the x and y. And theta is the orientation. Theta is the orientation. So we can further decorate it as you have the x direction, y direction 0, and you have the orientation. This orientation is this guy. This is theta. The theta, right? So you have x will be three-dimensional vector, right? X, y, and theta. That's your coordinate. Okay, this is your coordinate. Now you see the problem. How can you write the joint distribution? What is the joint distribution? Joint distribution means finally, I want to know about the p, x, y, theta. Right. In shorthand, it's just the p of the capital X, right? If x is a random variable, you want to choose, right? The value you want to choose, because it comprises of three-dimensional data, right? And this value x is not a random variable; it's in R3, right? It's a three-dimensional space. So we need what? We need a tessellation of a three-dimensional space. Right? We separate the whole environment to x, and maybe this is y. Sorry for the drawing. This is theta. Okay, this is the x, this is y, theta. What do you mean? For example, we separate this x into 10 possibilities, right? This y as another 10 possibilities. That means we want to localize the robots only with a precision of, let's say this is a 10 meter by 10 meter. So we only can localize at 1.0 meter in precision. But I only want to say, okay, the robot is in this cell. Okay, we need this, right? We need this because we cannot show the probability over this continuous space easily, right? So that means we want to, firstly, in 2D, we have x and y. We already separate the space into 10 by 10 grid world. And where is the robot? Probably the robot is here. Is here. And then we have what? We have a probability, right? We say I have 0.7 probability at this location, and probably 0.1 here, 0.05 here, 0.01, 0.01, etc. Right? Here I have the probability probably close to 0, right? And not possible to be here. So every cell you need to grant the probability. And what's the key feature here? The key feature is if you compute the sum of all these blue numbers, you will have 1. Okay? In this case, you get what? You get the joint distribution of xy, right? Joint distribution of xy. So that's the case where your state is in the 2-dimensional world, right? So if you elevate that to a 3D case, so in a 3D case, that's basically, this is R3, right? I separate this x direction to 10 possibility, y to 10 possibility, and theta probably also in, I don't know, 5 or 20 different possibility. As you know, the orientation of the robots can range from 0 to 360 degrees, right? 300 degrees. If I choose 10 possibilities here, then my resolution for localizing the head will be what? The resolution will be 360 divided by 10, right? 36 degrees. This is a resolution I can guarantee. Okay. If I want 1 degree orientation resolution in the localization, I need to separate this axis, theta axis, into 360 separations. Okay. Then you do what? Then you take out any of these cell. You take out a cell, and you do what? You will write a small number here, right? Probably the robot is here. I will write the number 0.6. And in the other places, probably here, another block, it's 0.12 or something, right? I need to write all the numbers across this 3D space. And that's what we call a joint distribution of x, y, theta. Okay? That's what happened in the 3D. What happened in 3D? So consider the case we discussed as a UAV. You can see now it's much more complex, right? It's not in 3D, not in 2D, but it's in 20D. The dimension is 20 dimension. So can you draw a 20-dimensional table? And for each cell in this 20-dimensional world, you will write in a number, and you sum all this number up, you get 1, right? So it's a huge. This is a huge space, right? This is a huge space. Even we simplify this problem, let's say we only have 10 cases for each dimension, right? Like for your x direction or y direction, you only have 10 cases. We already simplified the problem a lot. For the orientation, with the 10 cases, you only can guarantee 36 degrees of the resolution. Right? Your precision cannot be go beyond the 36 degree. Even you do that, you need how much of this memory, right? You need this much of dimensions. It's a 10 to the power of 20, right? 10 to the power of 20. You need this much of dimension for the memory. Okay, by subtracting the current location 1, right? Subtracting the previous location 1. So this is the cases you need to infer, right? If you can reject all these 99999 these cases, you will get the final confirmed case, right? So we even simplify the problem a little bit more, right? by removing 1 case. So still, it's a huge number for you to track. Okay, that means every time you grant a new control or you have a new reading from a sensor, some of you sees, okay, there is a camera here. Here is a camera. You get a new picture to the camera. This picture to the camera. You need to update that, right? You need to update this huge amount of memory space. It's not trackable, right? There's no way to track this huge joint distribution. Okay. But why do we discuss this joint distribution at all? Because we like it, right? We like this one very much, right? Why do we like this? Because if you have this joint distribution, you can have, okay, I want to know the current x position. I want to know about the current velocity. I want to know about the joint distribution of x, y, z. So I have all this information, right? As long as I have this joint distribution. So we like this guy, but we hate this one, right? We hate this one. So one thing to further analyze this space is what we can recursively apply this Bayes rule, right? Recursively apply this Bayes rule using the simpler example is like this one, right? So if we want to know about the pxy, so how can you know the pxy is actually the p of x times the py given x, right? Or y given x. So I can look at px. What is px? If I collect all the probabilities here, then I can have a histogram, right? I can have a histogram over the x dimension. Then I have this px, right? Just look at this map. Finally, I have a higher probability here. Okay, I have this distribution. So this is the px. This is the px. Good. And then what? I will look at the py given x. That means what? I will take one x value. Let's say I take out x value. Takes x equal to 1, for example. I take out this value. 1 in this case is the small x, right? This is the value. This is the value, taking the 1. So that means I will take out one of the columns, right? Sorry, it's not a column. It's a row, right? Sorry, it's a column. It's a column. It's a column. I take out where x equal to 1. I look at the distribution of y given this big X equal to 1. Okay? Then you see this distribution. Right? This distribution is another histogram, right? Maybe you get some position here, and all the rest will be 0. Right? Other places will be 0. So you have the P of Y, and that's the direction of Y. Right? And the other place will be 0. So that's also distribution. Okay, this is clear, right? Then the joint distribution is I need to multiply all these cases. And that's how you finally compute this joint distribution Px1. Okay. So that's related to many products like this one. You need to do a lot of products, here. And you need to do that not once, but many times. Anytime you get a new signal, you need to update. So the complexity is very high. Right? This is the complexity very high. So how can we solve this problem? We can assume that, for example, some independency. Like in the previous page, you have the px need to multiply with the py over x. Right. What is py over x? Py over x is if I give you this x value, if I give you this x value, then what's the probability of y given x, right? Finally, you get a distribution, right? Right, okay. And this guy, if you can replace that by py, then a distribution now becomes a number, right? Distribution becomes a number. That helps a lot, right? So px times py given x, if that's the, I don't have this assumption, sorry. For example, this is Vx, right? Vx will depends on x and y. That means you're given the position x and y at every location, you have the probability of Vx. This is the P of Vx given x and y. So probably you have a small bump. Right? This small bump happens in 3D. In 3D you have a bump. Okay, you need to store that in a 2D matrix. Right? You need to store that in a 2D matrix because this is 2D. So you need to store this one in a 2D matrix. Okay. Instead, if you can replace this PVX given XY PVX, that means the velocity of the UAV is independent of the position. You see, when the UAV is flying around, probably the current velocity is regardless of where it is, right? If you take this assumption, that means we can remove the dependency on XY. Then this PVX is what? Now it becomes a one-dimensional. It's a one-dimensional case, right? It's only an R. It's not saved in the 2D matrix, right? Because we don't have these conditions. Previously it's a 2D matrix. Now you only need a real number. One real number will deal with that. Good. And with this simplification, let's say velocity is nothing about xy, and rotation nothing about xy. See, previously we consider all this, right? Previously we consider all these variables, they should be dependent. Why that? Because following the recipe, PABC is a PA times a PB given A, and PC given AB. All right? We don't know what's the physical meaning of A, B, and C, so we can only write out this giant equation. And now we can make use of the take advantage of the physical assumption. So the velocity is nothing to do with the location, and the velocity in Z is nothing to do with the velocity in X, and the rotational speed is nothing to do with all this. Then you have this final deducted version, right? Reduced version. Then the space complexity is much reduced, right? Is much greatly reduced. Okay, so finally, you can see this equation is also a joint distribution. We like this joint distribution. Similarly, also we like this one, right? This one is very easy to compute because it's tractable, right? You don't need to update so many states. I don't need to update so many states. So how could this happen? It's based on these conditional independent assumptions, right? Conditional independent assumptions. So this is the key to save the storage in the computation. That means we need a structural representation. Right? For the probability reasoning, we want all this joint distribution. We want to use the independence assumption. We want to intuitively see the structure. Besides that, also we respect the algebraic formulation. We want to find the one-to-one mapping to this. And also we need a graphical representation. Right? So that's the stimulus of how could we further explore the independency, and we have the need of the graphical representation. So the aim is to have a diagrammatic representation of the joint distribution. Okay, so that means the graph sometimes, or most of cases, is to describe this joint probability distribution. And we want to represent the dependency structure and the nodes and edges representing a variable and dependency. We have different forms. You have a DAG, a directed acyclic graph. This is called the DAG. You have a Markov random field, which is an undirected graph. You don't have arrows pointing here and there. You have a factor graph. You want to define the functions on the edges, and you have a chain graph, right? Chain graph results directed cycles. We have different forms, right? We have different forms. If you are provided a graph, you want to know about the algebraic representation. Also, you want to convert something back, right? From the graph, you want to know about the equations, right? And also from the equations, you want to know about the graph. Also, their models may not be represented in the graph, okay? Good. Let's look at this example. So the previous graph, let's jump to this one. The previous algebraic formulation, a simplified version, you see this one will save a lot of memory. And then what's the graph? Right? Because we said that this Vx is independent of x and y. So you see x, y, they're separated somewhere else, right? It's not connected. And the Vz or Ry, so they have their own origins. Right? These are like the parents of other nodes. Okay. Let's start with the simple form. The nodes are defined for variables. Edge are the dependencies. And in the sense of DAG, directed acyclic graph, you get these examples, right? If we want to decompose ABC, by Bayes rule, you can have this one. Bayes rule, you can have this one. And when you write, when you draw the graph, so it looks like it's one on the right, right? So you have PA is a parent without any condition or nothing, you get a PA, right? And the B is depends on A. So given A, you have an arrow from A to B, right? And C depends on A and B, so you have an arrow from AB to C. Okay, so you have this one-to-one mapping, right? So it's like if you write PA times PC given A and PB given AC, with this decomposition, you have PA is a circle node without any parent, and the C is given A, and they have B is children of A and C. Okay, so these two graphs are a little bit different, right? A little bit different. And with the conditional independence, for example, given so A and B if they're independent, A and B if they're independent, then PB given A equals to a PB given A and B are independent. So this one. So you have PA, PB, and PC given AB, right? So PA, PB, and PC given AB, right? So if you have a joint distribution, you have this one-to-one mapping or one-to-one translation from a graph to equation. Good. So the key is to find out this joint distribution. As we said, a graph is always the tool to compute the joint distribution. Now, how can we compute the joint distribution? The equation is easy. We just find a product of all these sub-nodes of nodes and the parent of nodes. Right? Product of node and given the parent of node. Okay, that implies that how do you define the parents? If you have A to B, then A is one parent of B. Right? So it depends on the directed edges, and since we don't have a loop, right, it's acyclic. acyclic. So we don't have edges. Okay. For the joint distribution, you only have one variable on the left every time. You only take out the one variable on the left. One on the left every time. Then you can translate a graph to a joint distribution. Okay, and this translation is this translation is also feasible. There are additional elements for the graph, like previously we said you have a door, whether the door is open or closed, if it's the state of the door, and that's the sensors. It can be drawn as a plate representation. This is called a plate representation. Okay, the O will be repeated n times, right? Plate representation. And also you can use the dot to represent hyperparameters. Dots represent hyperparameters. If this guy is a Gaussian distribution and this one is the variance. So PS is a state. We have observation O. O has some variable which is the uncertainty of the variance. Whether if it's the variance. So you can draw this variance. You can draw this variance here. Denote that with a dot. Another thing is you're seeing is observed variable. You can dash or shadow these variables so that it means you can have a direct observation. Observation. Okay, in this case, you have PS given O. PS given O proportional to PS times the PO given S. This is what? This is the PSO. Right? This is a joint distribution from this guy. Right. Okay. Here are other examples. We have discussed the door detection example, the door state of the door, and that's the sensors. If you have additional sensor, all these are observable, so that's why it's a dash, right? With a different color. Okay. So much about the elements. And then what is important is how can we do the analysis over the joint distribution. Right? If you have 5 variables, and that's your equations, algebraic representations. This is the graph. So you have one-to-one translation, right? One-to-one translation. Based on what? Based on these assumptions. This assumption tells A and B, they're independent. This sign, just call that independent. Independent. And that's a conditional independence. Given B, D and AC, they are independent. Right? Given D, A, D, given B, D and AC, they are independent. Okay. So that's your assumptions. So these 3 parts, actually, they're referring to the same conditions, right? Referring to the same conditions. That's some important assumption. So then we have, for example, given the D, F and B, they are independent. Okay. Given the D, this one, given the D, F and B, they are independent. Given B, E and F, they are independent. You cannot directly see that from this assumption anymore, right? But from the graph, given B, F, and E, they are independent. This is something you have, right? Then given F, given F, A and B, they are independent. Why that? Because even if given nothing, the A and B are independent. Right? Also, this F is a descendant of B, right? It's like if you consider that the information passing the scheme, so the information source of F are coming from B, right? So B is the parent, the grandparent of F. So given this F, this F doesn't provide any further information about the relation between A and B, right? So it's not helping A and B. That's why given F, A and B, they are independent. Also A and D, they are independent. Okay, that's something you have. That's something you can see from the graph. What is important is this part, right? You don't have this, right? Given C, A and B, they're independent? No, right? You don't have this. We don't have this. We can finish this part and then we have the class over. So you can understand this as what? We said you have a door and you put a sensor on the door, right? A sensor on the door, and now you have a secondary sensor, so the T. Then given the D, given the state of the D, S and T, they are independent, right? Because they are just mirroring the state of the door. On the other side is what? Like the example A, B, and C here is I have two doors. I have door 1 and door 2, and with the same sensor S. What does it mean? S is a measurement. You probably have a sensor on the door or sensor on the robot. I see something, for example, I see the small z. That means I detect the door is open, right? I see a door is open. And if D1 is not opened, will that increase the probability that D2 is open? Yes, it will increase that, right? So that means the state of D1 and D2, given the knowledge of S, these two random variable, they start to be what? Dependent, right? They are not independent, they're dependent. Because if I see something, this something Z, this knowledge of Z will reveal some of the relation between D1 and D2, right? If D1 is not opened, then probably the D2 will be open, right? This probability will increase. So given C, you see the arrow, given C, A and B, they will be dependent, right? Similarly, given E, A and B will also be dependent, right? Given E, F and B, they will also be dependent. Okay, given E, C and D will also be dependent. So, seeing that I provide you, I give you a graph, and I can ask a lot of questions. Right? I can ask so many questions. So how could you guess the correct answer about these questions? Right? You cannot do this kind of analysis every time, right? Probably it's too complex. Right? You think of, okay, I have two doors, one sensor, then they will be dependent. Okay, how about the case of the E and the BF? E and BF. So E is the sensor, B is the door. How about F? F is another sensor. Okay, given one reading, will the door and the other thing will be related? Yes, it will be related, right? They're not independent. So this kind of analysis is too complex, right? Too redundant, right? quite redundant. So there will be certain tools to analyze on this Bayes network, which is called D-separation, right? D-separation. That's exactly what we will introduce next. So I think that's much for today. If you have questions, please stay and type them on the chat, or you can fire up the voice or with your hand. Otherwise, anyone else can leave, right? So we have the see you next week. See you next week.